are the two choices that you want to set A equal to. In other words, let's say under some conditions you want A to equal B point K, and under some conditions you want A to equal 0, or something like that. You can have in here an argument. You could have 0.3 times B point K. You can have an operation. You can have a constant number, or you can have a variable, or some combination of variables. But at any rate, what the clip function does is it sets this variable equal to one of these two things, depending on these two things. And again, these can be numbers, variables, or operations. Let's take, for example, the kind of thing. Let me give you an exact example. You were trying to harvest deer when they were over a certain amount and not harvest them when they were under a certain amount, right? So you had two possible harvest policies. One was to harvest no deer, and one was to harvest the excess deer. Let's call it some maximum deer population. Okay? So what you're telling, this is the deer harvest rate in this case, DHR.KL, rate equation. You're telling the computer to take away deer, this many deer, under some conditions, and no deer under other conditions. Now, how do you set up the conditions? The basic rule of a clip function is if argument number 3 is greater than argument number 4, you choose policy 1. If it's less, you choose policy 2. Now, how would we set that up? What would we put in here so that when the deer population was too high, we would harvest deer, and when it wasn't too high, we wouldn't harvest deer? You could put time point K in, and that's what you did when you had a time-dependent policy. When the time got beyond the time you set, you turned the policy on. But in this case, you don't know what time it'll be. You want to set up for any and all time the fact that if the deer population gets over your threshold, you're going to take away the difference. And you don't know what time that might happen. In fact, what you wanted to do is turn that policy on any time the deer population gets too high. So you wouldn't pick time. You can, in other conditions, put time in.
It doesn't work, because that's really high at time gain in deer harvest time.
It doesn't work, right. Yeah. Okay. Now what you're saying, what this equation says, when argument 3 is greater than argument 4, in other words, when the deer population is over your threshold, you choose path 1, and that means you take away the difference. If the deer population is less than your threshold, you don't do anything. You don't take away any deer. And that is one way of answering that last question on your assignment. There are other ways in Dynamo to do that, but that's how a clip function works. Just keep in mind, if 3 is greater than 4, you choose 1, and if 4 is greater than 3, you choose 2. I don't remember. I'd have to look it up in the Dynamo manual. Which is it?
It's greater than or equal to.
Greater than or equal to. If 3 is greater than 4, choose 1. That's all you have to remember. Yeah?
One of the hassles I ran into with that thing is that you can't use it in the level statement. So how would you go about saying, like, you want, say you had an equation relating the predator population to the density of the deer population, or something like that.
Yeah.
You want the predator population to zero up to a certain time, and then all of a sudden introduce predators and have them related to the deer population.
Okay. In that case, you want a time-dependent policy. You want to turn it on at a certain moment, right? And so in that case, you would have time point K here, and the moment, let's say that's the policy time that you're going to set there. And whatever policy you want before the moment you turn it on will be, say, 3 greater than 4. It would be here, and so on. Yeah. Oh, you want that in a level statement. I think what you have to do is set a rate that affects the level. Levels can't be affected by anything except rates. That's why it wouldn't accept that. A level statement in dynamo has to be level point k equals level point j plus dt, rate minus rate, or rate plus rate. But in fact, I think logically it should be that way. What you really want is the predator population's birth rate or death rate to be dependent on deer, not the predator population itself. Because that's the way the real system is. It isn't the population that suddenly changes, it's this birth or death rate that suddenly changes.
Yeah, but I wanted to simulate the introduction of predator population.
You just want to throw predators back in again. Okay, there you should have made predator population some sort of exogenous function like it was, only not a function of time, function of something else. We'll talk about it later. I have to get on to epidemics. Yeah.
Well, is flip a function that you can use anywhere?
Yes. There are other logical functions like that. There's a max function where you pick the larger of two things. There's a min function. A lot of things that I haven't taught you in terms of special functions. There are sines and pulses and junk like that. You don't need that for any of the assignments. If you know a table function, you can do anything. Anyway, you could have done the same thing with a table function. I'll let you figure out how. If you can write a table function, that's really all you need for this class. In Engineering Science 34, you will learn all the glories of dynamo, but you don't need them here. Okay. Your next assignment is on an epidemic model. In fact, your next two assignments, what we're going to do is show you a dynamo model of an epidemic model, and then Bob Norman will show you a stochastic model of an epidemic, so you can see how two different modeling techniques handle the same general sort of problem. And rather than just lay the program on you, now that you're much more sophisticated in modeling, I thought what we might try to do today as a class is make the epidemic model as a group so that you can see how you might start to put such a model together. And then there is, of course, already a written model which you can call up to do your assignment. But before I talk about that model, I'd like to at least think about how you would begin to make an epidemic model. And the facts that you need for the model are included in the little handout on the yellow fever exercise. It's just 3 pages. Why don't you read it through real quickly? And if you get done before I start talking again, try to sketch out. I'm asking for what? Right. A graph of how the system behaves over time or how you like the system to behave over time. But a graph of what? That's what David's asking. What are you plotting? Deaths? Deaths against time. Or infected population against time. Let's put both of them on there. You can put a lot of things on reference mode. Let's take infected population first. What would that look like as a function of time? Just general behavior. I don't need precise numbers. Somebody want to wave their hands in the air and show me how it's going to behave? Yeah.
Well, it starts out at 22, and then it goes up.
Okay.
Goes down, and then it shoots up.
Those were the cases of sickness, right? Or was that deaths? That was deaths. It looked something like this, right? Whoops. Something like that. What about sickness? You don't know, you kind of got to guess. Yeah, Dave?
Well, there's a positive feedback on infection, so I would expect that it goes up until a negative feedback of being immune or dying.
Okay, you're already into the causal diagram. But if this is deaths per day, let's say, something like that, the deaths are probably some rather straight function of illness, maybe a delayed function. Could be. Let's make a guess and say, and furthermore, everybody who gets yellow fever doesn't die. A lot of people get better. So maybe the infected cases is something like this. This is in people infected. Something like that. Okay. That's at least a good start for reference mode. We might, as we learn more about yellow fever and so on, we might make that a little more elaborate or more correct. But it's a good start. Yeah, did you have a question? This is one epidemic, right. And over a long time horizon, you don't know it from the reading. Maybe you could have a long period in which nothing happens and then another epidemic. And that's something you might think about whether you want to include in the model or not. But for the moment, let's start at least as simple as possible and just make a model of one epidemic, of the dynamic behavior of one epidemic. And later on, I assure you, I will give you a chance to do a repetitious epidemic. Okay, now let's take that as a reference mode. How do we make a causal diagram, a beginning hypothesis of the connected factors that make a system behave like that? Does anyone want to suggest at least how to start? I don't need a whole complete diagram from one person, but how do you begin? Yeah.
Mosquitoes on one side, infected persons on the other with causal loop between them.
Mosquitoes. How do you spell mosquitoes? And infected persons. And a positive loop between them. Meaning as mosquitoes go up, infected persons goes up. Is that what you... And as infected persons goes up, mosquitoes goes up?
The other way around.
The other way...
I think it's the other way around.
The other way around is the same thing. Or do you mean a minus sign? Infected mosquitoes and regular, and infected persons and regular. Okay. So we need all those things. So we've got regular persons here, right? I'm going to put them all up, and then I'll ask you how to connect them. Let's take those connections out for a minute. Okay, and you also want infected mosquitoes. I won't write the word regular, but we will understand it. Mosquitoes. All right, there's 4 things. How do we connect them?
The positive loop between the infected mosquitoes and infected persons.
So more infected mosquitoes, more infected persons, plus more infected persons, more infected mosquitoes, plus
More infected persons, fewer persons.
more infected persons, fewer persons. Let's call these what, we don't really mean persons, we mean not yet infected persons or something like that, right? Healthy? Healthy. All right. Healthy but scared, right. Okay. Any other connections you would like to see there? Mosquitoes going to infected mosquitoes. What's the sign? Immune people. Where do you want them? And how do you want them connected? Immune people? And how are they connected? More from to here? This way. And positive from immune to healthy. I detect a note of dissent on that last arrow. What do you mean by that? Do you mean that after a person is immune for a while, he becomes unimmune? The more persons you have. Oh, okay. We're having a word problem here. What we meant by healthy here was healthy but vulnerable, right? Those were people who hadn't yet been infected. At least that's the way I heard what you were saying. Which arrow is going the wrong way? You start out healthy, then you get infected. And now Joel is making circles in the air. Okay, let's think this through one more time. In fact, this is a good example. It's fun to make these things as a group because you end up having to explain things as you go and define things differently. Now we've defined 3 kinds of people at least. We may end up with more. There's people who haven't had yellow fever and who could get it, right? There's people who've got it. And then there's people who have had it and are not able to get it again because they're immune. And then there's dead people. Okay, so we need another kind of people.
They're immune too.
They're immune too, all right. We might want, for purposes of our model, to keep track of how many there are, though. So let's keep them separate. Okay, now let's think about the process by which these people move from one category to another. You start with healthy people, and there's an arrow here saying that as people become unhealthy, there are less of them. That is, as people move from the vulnerable category to the infected category, there are fewer people in the vulnerable category. That's what that arrow says so far. Does anybody want me to take that arrow out? All right, now the suggestion is there's a positive arrow. Why? What is your causal thinking there? And what this says is the more healthy people, the more infected people. Or possibly the less healthy people, the less infected people. Do you want that in there or not? The easier it is for a mosquito to find one to bite. And let's think of the extreme case. Suppose there aren't any vulnerable people in the population. What will happen to the infected people? Okay, so there probably is a connection, both ways. Both ways. It seems to me that arrow makes sense, at least at the point where this gets near 0. It's going to stop the flow into infection, into the infected category. And certainly as there are more infected people, that's going to take away people from the healthy ones. Bob?
If you use the category that's lowest on the board, you're describing people both as healthy and vulnerable.
Yeah.
I think you're now describing it more as vulnerable.
Yeah. Let's call it vulnerable. As a matter of fact, it is. No, you don't. We'll be able to translate. Yeah.
I think there's something important missing from the data here, and that's whether or not a person who's immune to the disease can transmit it, whether he just doesn't get sick or whether...
Let's assume, from my vast knowledge of yellow fever, that an immune person does not become vulnerable again and does not transmit the disease. That makes things easier. I don't know if it's true, but it makes things easier.
That's partly a choice of time.
Yeah, that's true.
Also, is the disease transmitted only by mosquitoes, or is it transmitted through human beings?
No, only through mosquitoes. That is true. The disease is only transmitted by a mosquito biting an infected person, in fact, before the infection becomes apparent, and then biting a vulnerable person. Why is there a direct arrow? Oh, I see. Okay. Everything depends on the mosquito, so you think that this part of the loop is sufficient. Okay, I'll take it out. It's your model. Let's think about this in terms of behavior, because sometimes that helps when you're not quite sure what to do in your causal diagram or what relationships you really want in your model. I mean, there are a lot of other relationships we could put in that we haven't talked about. At the moment, I see one clear positive feedback loop there. And it seems to make sense to me. The more infected mosquitoes you have, the more humans are going to get infected. And then the more humans infected there are to bite, the more mosquitoes will bite them and carry the disease further. Now, suppose that's all there were to the system. How would it behave? Right. It would go up forever. And that's not what our reference mode does. That's why it's handy to draw the reference mode first. On the other hand, there is a sort of exponential looking part of that behavior. So you might say that in this part of the behavior, it's that positive loop that's dominating the system. Now, what I would like to know is what causes this part of the system. What causes the epidemic to stop? Everybody gets immunized or dies. You run out of vulnerable persons. From the point of view of the mosquito, you have a non-renewable resource, right? You've run out of vulnerable people. Have you got that in the model? Yeah. You haven't run out of mosquitoes, or at least I haven't heard. Maybe you've run out of mosquitoes. We might think of that too. We haven't got anything affecting the number of mosquitoes at the moment.
Yeah, cold weather.
Cold weather. Sanitation. There. Policy. One of the policies you might want to test in the model is changing the number of mosquitoes. Yeah. You could start that way. If the epidemic only occurs over a few days, then the weather may not be very important. Depends. I mean, whether you put that in or not depends on what you want to get out of the model. But I don't think, well, maybe it is. Is that what's caused the downturn in the infection rate? Yeah.
Well, mosquitoes live for only 18 days.
Right. So, you want a mosquito death rate in there? You want a mosquito death rate. How do you want that connected?
It's cyclical, so
The negative, feeding it to total mosquitoes.
Yeah, but it says the mosquitoes is current.
I'm sorry, I have to just generically complete that feedback loop. Every time I see a death rate, I know there's got to be a feedback loop, right? The more mosquitoes there are, the more mosquitoes die. Okay. Okay. Mosquito birth rate.
Didn't they say that was constant in the...
It says it's current. They always don't die.
You can make, there's no one right way to make a model. You can keep it constant if you want to, or you can model the mosquitoes explicitly. That's fine. Yeah.
I want a loop showing that people take precautions against being bitten. Other people are getting bitten.
Okay. So, I noticed dissent throughout the class. Let's pursue one thing at a time. I still want, we had this suggestion that we're going to run out of vulnerable people. And we've got one arrow indicating that we're going to run out of vulnerable people, but we haven't got anything saying that when we run out of vulnerable people, anything else is going to happen in the system. What do we do about that? Okay. What kind of a sign do I want on that arrow? Where have I seen that before? What does that whole loop say? Let's not talk about each individual arrow. That whole loop between infected persons and vulnerable persons. But basically, what's that saying about the system and how it's connected? Yeah.
They'll control it that way really quick. It's closed.
It's closed.
You need a level of those little things that says start the population, which is just a line and circle.
Okay. Essentially, I think that is saying, at least if we model it right from in the next step, that exactly what I heard as a hypothesis in the class, that we eventually will run out of vulnerable people. Because as the infection rate goes up, we're going to be taking people out of that category, and eventually that category is going to get so low that as this comes down, this comes down. We have to have that in there. It's essentially a people accounting mechanism. Is that what causes the decrease in the epidemic? Or is that the only thing that could cause a decrease in the epidemic? Yeah.
As the infected person goes up, the dead person will
As the infected persons go up, there are more dead persons, and that will decrease the vulnerable people. Everybody like that? Why?
It's redundant.
Where,
When the infected person goes up directly, the person becomes infected, he's no longer vulnerable.
right. The people who are dying aren't the vulnerable people. They're the infected people.
So put the arrow back down to it.
So put the arrow back down to infected people, right. How about here, too? Look at all those negative loops. We have to have them, you know. Every time you find a positive loop, you've got to have some negative loops. Otherwise, you have infinite growth forever. And so any one of these loops might stop that epidemic, maybe all of them together. Yeah?
Shouldn't immune persons be vulnerable persons instead of infected?
Anybody want to answer that question? Should immune persons go to vulnerable persons instead of to infected? Who?
People that are immune are no longer vulnerable.
Right.
It's a negative arrow.
Think of it, this gets confusing because we're not modeling the flows yet. In the next stage when we make the dynamo diagram, the flows will become clearer. We're beginning to talk very clearly now about a people flow. You've got vulnerable people. They get infected by getting bitten by mosquitoes, and they go into infected category, which therefore decreases the vulnerable category, right? Because people are moving into this category. And infected people can do one of two things. They can die or they can recover and become immune. And if they do either of those things, they move out of this category. And therefore this category gets depleted, and that's what that negative arrow and that negative arrow mean. But in becoming immune doesn't deplete vulnerable people, it depletes infected people. And by becoming infected, you've already depleted vulnerable people. Is that clear? Yeah.
You need identification of people being born, because otherwise there's just a sink, and then what source for vulnerable.
We could have born birth rates and death rates connected to all those population rates. It depends on our time horizon. On 18 days, maybe we could leave that out. If we're running it for 18 years, we certainly would want it. We might even want migration. Maybe everybody leaves when there's an epidemic. There's a lot of things we could put in here. I think that's a good start. The thing to do with a model is get something that you think begins to make sense, get it running, and then you can add lots of stuff later. We haven't got a vaccination policy on there. We haven't got the fact that people might leave the city when an epidemic starts. There's a lot of things we can add. And of course, I will be delighted if anybody in doing their assignment wants to add stuff to the model that isn't there. That's fine. Be my guest. But let's start with that. Do you think that just that much is going to give us something like our reference mode?
No.
Why?
Still haven't specified what that dominant negative feedback loop is down at the end.
What is the dominant negative feedback loop that brings it down at the end? Could it be any one of the three negative feedback loops we've got? If not, what is it? Why, since you're doubting it, why don't you tell me?
I would say it's either one of two things. It's either what Bill suggested, that the precautions taken by people when the population starts becoming infected, or has to do with wet season, dry season, and maximum climate.
The weather driving it down.
It doesn't seem to be a matter of days in the one they show. It seems to be a matter of 3 months.
3 months.
And that
Yeah.
does make it, it ends in September when
Could be.
weather gets cold and things dry.
Could be. Let's try it. We can add that in. And the thing I do when I'm starting to make a really new model and I don't quite know what's going to happen is all the ideas I have I make a list of. And I start with the simplest thing and see if it works. And if it doesn't, I start adding things from my list until I've got something that begins to feel right. And feeling right is ultimately, don't let anybody ever tell you different, the way a modeler finally decides whether to believe his model. And I'll talk much more about that on Monday. We haven't got much time left, so I'd like to explain the program. And there's a handout you should pick up as you leave, which has at least a beginning program. If you don't like it, please change it. It's a pretty simple one of really those feedback loops and nothing more. And that's the program you should at least start working with. And there's a couple of tricky things in it you haven't seen yet, so I'd like to... Actually, Greg, could you pass these out now so that everybody can see them? Somebody, George, you want to have somebody help? It looks complicated, but in fact, it's in some ways simpler than the deer model. It's complicated because the flows of mosquitoes and persons are represented in quite a lot of detail. One thing that I thought was important was the delay times, the incubation periods, and things of that sort. And I wanted to get those in, and so I put it in explicitly. There's a mosquito flow up here, and there's a person flow down here. Let's take the person flow first, because we've talked about that. There's a level of vulnerable people. They become infected and go into an incubating people category, which means they haven't yet got the disease, but they're about to get it. Then there's a contagious category. In this stage, if they get bit by a mosquito, they transmit the yellow fever germ to the mosquito. Then they become visibly sick, and then they can go one of two ways. They can become immune or they can die. And in the mosquito case, I've taken the suggestions of the author, which you are free to change. In fact, I ask you to change it in the assignment. And have made a constant mosquito population which generates a certain number of new mosquitoes, a constant fraction of new mosquitoes each time period. And for a while, they're susceptible to biting someone with the infection and becoming infected. If they do so, they become incubating mosquitoes. It takes a few days before they can transmit the infection on. At the point where they become infectious, there's a very important connection here between the number of infectious mosquitoes and the actual infection rate of the humans. And then eventually the infectious mosquitoes die because they only have an 18-day lifetime. Now let me show you, it's not too obvious from the graph where the positive feedback and the negative feedbacks are. The central positive feedback loop that you postulated goes like this. More infectious mosquitoes, which is this level, increases the infection rate, which increases the number of people incubating and then finally becoming contagious. And if there are more contagious people around, the probability of a mosquito biting a person with the disease goes up. And that, therefore, increases the number of mosquitoes getting the disease, and they incubate it and become infectious. And that's the positive loop. It goes through a lot of information and a lot of levels, but essentially it's that loop right there. And the negative loops are all over. The loop that says that vulnerable people, I see there's a missing little arrow. Vulnerable people eventually run out should be an information link between VP and IR. You can add that. But it's essentially that little loop there. And the other is that people are leaving this contagious category. The more people are in there, the more leave. And they're no longer of interest to us because they're not propagating the disease anymore through mosquitoes. And then they can either become immune or die off. And the behavior mode of the model is shown in a standard run here. And you see the death rate actually goes off the scale and comes back down again. The rate in which people become infected is the little I. The vulnerable people eventually don't really run out, but they certainly get down to the point where the epidemic dies, and the immune people build up. In other words, the population gets less and less rich in people who can be infected. And as that happens, the positive feedback loop gets balanced. It really slows down to the point where it's not generating more infection all the time. Now let me show you a few things about the equations. I think most of the equations will be obvious. We start by going through the mosquito population. Equation 140 is the first level there, the susceptible mosquitoes. These are newly born mosquitoes. They have 18 days to live, and during that time, if they bite somebody at the right stage of development of the disease, they will become carriers of the disease. The birth rate adds to that level, Those who leave without being infected subtract from it, and those who become infected also subtract from it. And essentially, those mosquitoes that don't pick up the disease in the early phase of their lifetime, we just forget about. They leave the model. They're still around biting people, but they've gone out into a cloud here, meaning if they don't catch the disease early on in their lifetime, they won't be able to get all the way through the incubation to transmit it, so we don't care about them. What we want to pick up is only the mosquitoes that get the disease early on. And they start flowing into this stream of mosquitoes. Otherwise, they leave the model. Most of the mosquitoes in the world wouldn't be in the model, only the ones that are carrying the disease. We start with none in that level, and the first DT will add some mosquitoes through the birth rate. The birth rate is simply the mosquitoes times a constant, and the mosquitoes is constant, the birth rate is constant. You can change those. The mosquitoes that don't catch the disease are those that essentially have lived 3 days, and at that period it's too late. They no longer can go all the way through the incubation period, so we lose track of them, they go out. The mosquitoes that get infected, here's an important equation. These are the ones who pick up the disease. It's a function of the number in the level that are susceptible to getting infected, times the probability of its becoming infected, times the BDM is bites per day per mosquito. That's really the rate at which they're biting people. Now I've made the rate, just for fun, I've made the rate at which they're biting people a rather complicated function so that you can fool with it. All else equal, it's a constant equal to 0.2 bites per mosquito per day. If you notice on the chart, a mosquito only bites once every 5 days or so. Then it can exist for 5 days on that blood, and then it bites again. So each mosquito is biting on the average of 1/5 per day. This function is a random noise function. What this does is tell the computer to throw the dice, pick a random number. And I put that in just because I thought it might be random. A mosquito running into a person on just the day he becomes hungry. There might be a little noise in the biting rate. You can put a random noise function in anywhere, in any dynamo equation that you think has a random component to it. It's important here because our next model will really emphasize the random part of this system. I put it just so you can test it. A random noise function says multiply this number, 0.2, by a randomly picked number with a mean of 1. I set that. And a standard deviation around the mean of any number you choose. I start with a standard deviation equal to 0, meaning that, in fact, the whole random noise generator is turned off. It's not effective, and it's just multiplying by 1, and that function isn't important. If you want to turn it on and generate a random number, you just set the standard deviation to some number other than 0, like 0.1. That gives a 10% variation rate. Or 0.2, 20%, and so on. And I've asked you in the assignment to try that. That just adds a little random element to the model. The last thing multiplying the biting is sort of a density multiplier from human beings. That is, I've got like the predator assumption in the deer model, I've assumed that if human beings get killed off by yellow fever, they'll get harder to find, and therefore mosquitoes will bite fewer of them. And there's a table function that's dependent on the human population. It says, for example, if there are no people, there's no biting going on. The mosquitoes, I'll assume, don't get killed off under those conditions because they go off and bite cows or something. But at least as far as transmitting the disease, that turns it off very effectively. You can ask yourself whether that feedback I've put in there is really important in the operation of the model or not. In fact, I just added it this year. It wasn't there last year. And I'm not quite sure what it'll do, so we'll have to explore that one together. It just seemed very unrealistic to me not to have it in, so I added it. The rest of the model is pretty straightforward. The flow rates go on. The delay times in the flow rates are taken from your paper. For example, the incubation period, or the rate at which mosquitoes become infectious depends on the incubation period, which was 12 days, as I recall. So this essentially says mosquitoes becoming infectious, the rate, depends on how many are in the incubating stage, divided by 12. 1/12 of them come out of incubation each time period and become infectious. This is equivalent to a delay. That is only, the mosquitoes stay on the average 12 days in the incubating level, and then 1/12 each time period come out and become infectious. And that form of a delay is shown throughout the model. I hope that the rest is obvious. Just let me point out one other new thing. Well, first of all, the probabilities are important because they're in the middle of all the feedback loops. The probability of biting a contagious person is simply equal to the density of contagious people. Given that a mosquito bites somebody, and that's determined by that BDM, bites per day, whether they bite a contagious person, I'm assuming, depends only on the density of contagious people. This is contagious people divided by the whole human population. There isn't anything about contagious people that attracts mosquitoes or repels mosquitoes. Therefore, the probability is just a function of the density. The probability of biting a vulnerable person is the same. Vulnerable population divided by the total population. And one last thing, I've added a new kind of output statement so you can see a new sort of output. In addition to the plot statement that gives the plot I've shown, I put in a print statement, and I printed out all the rates. That's because I find it very informative to know what's going on in the rates of a model. Usually if there's something going wrong, you see it in the rates faster than anywhere else. All I've done here is list the things I want printed out and said that I want them printed out every 20 days. You can change that. You can add things if you want to see something else printed. The way the output looks is shown on the first page. This is the print. You can see the print is occurring every 20 days. And these are the values for each of these rates on each of those 20 days. You have to watch because sometimes the compiler shifts the decimal point and tells you at the top that this is in fact to be multiplied by e to the 4, in other words by 10 to the 4th. So it isn't 2.8 mosquitoes being born each time, it's 2.8 times 10 to the 4th. And that when it gives you a scale factor like that, it applies to the whole column. If you don't like that print, if it bores you, you can suppress it by simply writing print period equals 0. You can suppress the plot by writing plot period equals 0, or you can change the time period if you less or more often what the rates are doing. Okay, that should be enough to get you started on the next assignment. If there are any questions, come ask me or ask them Monday in class.